All right, so we have the privilege, or what have you, of navigating this discussion session and also being the only thing keeping you from lunch, which is outside. So we'll try to do this in a very efficient manner. Crystal and I put our heads together and just tried to look at themes that have emerged, starting yesterday, but then also this morning from the various talks that we've heard, which are all great. They've kind of fallen in three categories that we, threw together in no particular order, so just don't look at this as some kind of ranked list. We've heard themes of star formation efficiency, particularly at high redshifts. We've seen and heard about problems and methods to form black holes and also how they grow and then influence our galaxies. And then we've also been hearing about anchoring what we learned about from what we'll call local galaxies or low redshifts to higher redshifts and try to understand galaxy properties if they're similar or different. And these are just some of the guiding questions we've put on there. I think, Crystal, you wanted to say a few more words about the local galaxies and how they might tie into high redshift galaxies. So,
absolutely.
And
I've still got a mic on, so I'm good. Yeah, we heard a little bit from Andy Burkert and others this morning of comparing, some of the physics of high redshift galaxies to what's going on locally. And I wanted to show one slide really with IFU data that I think drives home some of the things we can learn from local galaxies here. So this is a composite HST image of a galaxy that's just 40 megaparsecs away. And, you can see it's a clumpy galaxy. There's some older stars over here, and there's a starburst region over here. These stars are like 2 or 3 million years old, and these stars are about 40 million years old. You map spectra all over an object like this with an integral field spectrograph like the Keck cosmic reionization imager. And this is a map now of velocity field, around those clusters. And what you find here is a biconical outflowing galactic wind. And I think a lesson here, right, is that it's not driven from the starburst region. The starburst region is too young. It's only a couple million years old, and most of the supernovae that those clusters will produce have not gone off yet. And it's the older clusters over here making the outflow cone. I think this is really relevant to how Lyman continuum radiation gets out of galaxies. Because if we now go and look at the ionization structure in a galaxy like this, we'll get a different picture still. So let's see if I can get there. There it comes. Okay. So here we've got a map where in red, we've got hydrogen beta emission, in green, oxygen-3, 5007, and in blue, helium-2, 4686. So as expected, the hard ionizing source, most of the ionizing photons, are coming from that young cluster, and that's very much not where the wind is. And if we map now the ionization parameter in 032, we get up to very high ratios, 12 to 14, numbers that indicate high ionization parameters in this region up into here, where these contours go. So it's like where the ionizing photons interact with the outflow cone is the direction where this 032 ratio is actually increasing with radius and is maybe a candidate direction, for like where Lyman continuum would be leaking out. So, in my mind, clumpy galaxies are interesting for an additional point that they can have different ages, and those clumps can help solve the timing problem of getting ionizing photons out where you have to wait for galactic winds to develop.
No, it's great. And certainly that's something that people in this room are interested in simulating, and also some of us are interested in observing. So, with that said, here's the format we've tried to, as university professors trying to engage classes after a long lecture. We're hoping we can prompt some discussion by doing the following exercise. So we're going to ask you, with your neighbors, find a group, pick one of these topics, just one, and you can discuss and kind of figure it out. And then, you can either try to address one of these questions that we put up here to prompt you. Is it the ways that you think which of these are an important problem that you'd like to discuss with your neighbors? It doesn't have to be the most important problem. just an important problem that you'd like to discuss with your neighbors, and then trying to come up with what would it take to further our knowledge in this field, either new observations, new simulations, what do we need to address one of these questions, or if your conversation takes you to a new question we haven't considered, by all means use that. So, in the interest of time, we're going to try to keep this relatively short. So this is for everyone. Young people, don't be ashamed. Turn to your more senior colleagues, maybe people who have some salt in their hair, and you can try to engage them. If you're older, please turn to the younger people and see what they think. They may have new ideas. They are the next generation, so we would like to encourage that. Take about the next 5 minutes, figure out one of these topics that is important to you, come up with something, and then we'll return to class and see who wants to share that with the class. Go, 5 minutes.
I think we want to be particularly focused here on, like, what would it take to make progress and answer these questions. Yeah, yeah, you did. Yeah. Yeah.
Do we have alignment continuum of mission? Is it one of the